Okay, now I see.
Go ahead, Jose.
Good afternoon, everyone. We are here today. We are having our architectural practice community of interest webinar sponsored by our community of interest. We have our webinar is about acoustics, called In Pursuit of Acoustical Equity. Our presenter is Viken. You will hear more from him. He is an expert in acoustics. I'm really excited about this webinar because it's an issue that I have been experiencing in different projects and in my office particularly. And that's how I got connected with Viken. And I can tell you that you will be a lot more informed about the subject once we're done with our webinar. My firm is Guri Matute. I'm the Community of Interest, the Architecture Practice Community of Interest Education Chair. And my firm's located in Miami, Florida. Well, with no more to be said, I'm gonna hand the presentation over to Viken. Before that, we have some housekeeping items that we need to go over. Those connecting through a VPN will likely have difficulties. Audio is broadcast through your computer speakers. You should have been prompted to connect to the audio stream. Click connect. Use the chat tab on the control panel to submit a technical issue. Look at the private tab for your response. Submit a written question at any time via the Q&A tab that is on the right top right corner of your monitor. Upvote the questions already asked to avoid duplication, but indicate that you also want an answer. Click on the handouts tab to download a copy of the presentation slides after the presentation also. And the webinar will be recorded for future viewing at any time. So here is our presenter. Viken, you have the floor.
Thank you, Jose. I really appreciate it. So I'm going to take a second right now and share my screen.
Oh, we also have a little, we have a questionnaire for all the attendees to submit this question about who you represent. So.
Yeah, it's perfect. I think if people have the opportunity to answer that, that would be very informative to us. And so on that note, I'm going to jump right into it. Jose, yeah. I believe you can see my screen at this point, just a quick confirmation. Perfect. So let me start by welcoming everyone. I'm excited to be here. Our course is titled, it's registered with AIA, called In Pursuit of Acoustical Equity. So thank you to SAME and thank you to Jose and his firm for giving me the opportunity to show up today. If you have any questions regarding relating to the content of this course, I want to welcome you to reach out to me at the end of this presentation or even in the future. My email is presented on this slide and will be presented again in the future, towards the end of the presentation. So here we have the AIA CES provider statement. It indicates that the course is being offered by a registered provider and that you'll earn a course credit at the completion of it. So I'm going to take a moment here to introduce myself. My name is Viken, or Vic Kukunyan, and I'm a licensed mechanical engineer. I've actually had the good fortune to study a range of specific topics within bioengineering, robotics and mechatronics, and notably acoustics, a sub-branch of physics that focuses on sound, noise, and vibration. More than 3 years ago, I started working for a manufacturer of electronic systems for sound masking, music, and paging. In my role, I'm able to bring my experiences working in a number of other industries to the study of acoustics in the architectural environment. I'm glad to be part of an organization that understands the need to encourage research in our field and to make that information readily available. It is for this reason that I devote some of my time to developing acoustical standards, guidelines, and codes, where I try to marry acoustical theories to their applications. More specifically, I hold positions with the following organizations through which I'm able to help promote the importance of, the importance as well as the advance of scientific and civic literacy, which is why I have my own objective for today, and that's to help you establish a deeper understanding of acoustics. My hope is that you'll be able to walk away prepared and able to speak at the same level as acousticians without needing to be the expert. Now, I like to start my presentations with an overview because I believe a person's learning experience is greatly improved if they've provided a roadmap, or more specifically, if they're made aware of the important points that are foundational to the primary objectives. I'd compare this to solving a puzzle. If you know what the assembled print is supposed to look like, then you can be better able to expect to identify certain puzzle pieces and to anticipate where they may fit. This structured approach is critical to effectively communicating nuanced and advanced concepts, such as our primary objectives. Our first one is to introduce the concept of acoustical equity. And while the notion is simple, that is, to create a consistent acoustical experience for occupants, there's great value in understanding why it is needed to inform how we can provide it. The second, our second objective, we will have to develop the concept of acoustical equity, and we'll do that with the use of data, literature, and acoustical and psychoacoustical theory. Specifically, I will be discussing the correlation between occupant satisfaction with a space and its satisfaction with its acoustics, and the correlation between acoustical satisfaction and speech and acoustical privacy. I will then revisit first principles so that we have an accurate understanding of privacy and comfort. This review will clarify why traditional acoustical strategies are not reliable tools for design. Finally, I will devote special attention to the role of background sound, which is distinct from background noise in the built environment. I will explain the role of masking sound and how it plays in acoustical equity, which will inform how it has to be used to support the occupant's overall experience. We will need to refine our use of acoustical vernacular and recognize the extent to which different concepts depend on each other. And once these foundational principles are understood, an intuitive framework will become apparent, one that we can use for design as well as performance verification. So on that note, let's move on to our first objective. I'm certain it's apparent to us all, the start of the pandemic has intensified discussions relating to public health and safety. More explicitly, the world sought out guidance from subject matter experts on how to manage the spread of the virus. Early investigations identified airborne and surface contact to be the highest risk paths for transmission. For these reasons, many, if not all, spaces were retrofitted to allow for physical distancing, to allow for improved cleaning and disinfection practices, and to provide enhanced ventilation and filtration of air within indoor spaces. It is unsurprising that this people-first mindset has been a catalyst for the healthy building movement. Champions like IWBI and GBI, with their existing subcommittees of subject matter experts, were prepared since the onset of the pandemic to offer enhanced recommendations to safeguard our health and safety. Needless to say, they were also instrumental in informing new and more stringent minimum requirements, such as those defined by various levels of government. And as we continue to endure this new normal, we're seeing a new need for a deeper commitment to safeguard and improve our health and well-being, which aligns more closely with the original scopes and purposes of these standards. However, some experts were quick to identify the impacts that would result from enhancing the requirements of certain indoor environmental quality, IEQ, parameters on others, such as indoor air quality, IAQ, on acoustics. By way of an example, surfaces that can be easily cleaned and disinfected are generally hard and non-porous, which are qualities typical of materials having lower absorptivity performance. The adoption of these materials make an environment more reverberant or echoey, and potentially less conducive to certain tasks or activities. Another example is the enhancement of ventilation and filtration requirements, which may either require the installation of additional equipment or necessitate higher operating conditions of existing equipment that would expectedly produce higher levels of noise in a space. So while we can rationalize the need to make these compromises, the reality is an exacerbation of conditions of an IEQ parameter, acoustics, that already performs poorly. This is reinforced by the meta-analysis, which is a study reviewing the results of many studies by a group at Harvard of modern and sustainable best practices, such as the LEED standard. Dr. Joseph Allen and his group found that acoustics was the only IEQ parameter that did not consistently score better, and in many cases resulted with lower scores for satisfaction with noise. Now, these low ratings have added significance in today's climate, which is apparent in the conversations about maintaining a healthy work-life balance. While employees used to look for workplace amenities like a pool table, private chef, or other perks, their priorities have shifted since working from home, desiring and now expecting a higher quality of life. This is supported by results of surveys by firms like Gensler, which suggest, employees enjoy the benefits of working from home, which include, more time with family and friends, flexible work hours, and the benefits from not commuting. And while employers are certainly interested in bringing employees back into the office, there's an indication that employees also have some interest. In that same survey, 88% of employees, of 2,300 employees, responded saying that they'd like to return to the office, at least in some capacity. Some of the primary reasons being a need for a quiet and distraction-free environment, and the need to collaborate and socialize with colleagues. This finding is echoed by Steelcase's survey of over 32,000 people from 10 countries. The architecture and design community is tasked with meeting this reprioritization of employee goals, and they believe the notion of equity is the next solution, or perhaps the underlying theme of solutions for the IQ parameters. And while this makes sense at a very high level, it's impossible to execute if we do not have an understanding of the what or the how. And this is evidenced by Dr. Allen's study, which demonstrated that the results or the outcome were unreliable when we were using traditional acoustical design best practices. Now, the conversation around equity has been around for some time. One notable perspective that survives is the one echoed by the built environment strategist, Esther Greenhouse, who believes the environment has the power to disable or enable the person. And I'm sure we would all agree, the design and the performance of a space has an immediate impact on our health and well-being and on our abilities. Because if there's a poor fit between the person and their environment, the environment acts as a stressor, pressing down on their abilities, pushing them to an artificially low level of functioning. It is on that note that I hope to shift gears. Although we're able to, and we have acknowledged the need to consider acoustics, we need to revisit first principles to clarify what that entails. This is because good acoustics is widely, yet incorrectly believed to be an environment that has low levels of noise. To understand why this belief is widespread, we have to go back to the 1950s when there was a sudden rise in awareness for the need for policies for occupational health and safety. Among the many topics was the one for protecting auditory health. We started to learn that sudden or sufficiently prolonged exposures to high levels of sound could cause physiological damage to the auditory anatomy. This data allowed acousticians to develop models to predict the relationship, which have been used to establish safe limits for noise exposure. It is extremely important to understand that these calculations consider both level and time of exposure, because the relationship is not linear, which we can also see in the following table. For example, hearing loss may be instantaneous when exposed to a 120 decibel bursts of noise, or it may be considered safe if the exposures of 100 decibels and 80 are limited to 15 minutes and 8 hours respectively. These values are reported by NIOSH and calculate with reference to an 8-hour workday. Similarly, we can calculate a safe limit for exposure of a continuous noise for an entire day, which would be somewhere in the neighborhood of 70 decibels. What this means is that for lower levels of noise, and I say lower in contrast to the word low, the mechanics that cause hearing loss are essentially not present. But this is not how the general population understands this. This is because research does not discriminate on what is considered noise, and it simply assesses the impacts on the person. While academics were relatively quick to distinguish the difference between auditory and non-auditory effects, the general population has not. Some examples of non-auditory effects include cardiovascular disease, cognitive impairment, and annoyance. For obvious reasons, there's really no benefit to considering the non-auditory effects of high levels of noise because there are regulatory requirements intended to protect our auditory health. At this point, I'd like to revisit our acoustical vernacular, specifically sound and noise. Sound refers to all acoustic waves, while noise is sound that is generally perceived as being distracting, disturbing, or having some negative impact. This is important because we are constantly surrounded by acoustic energy. We are immersed in an acoustic environment, and the ambient conditions of each of those environments vary according to the space type, its function, the occupants, their activities, and our expectations. Although this is nuanced, there's great value in distinguishing between these two terms, and this becomes apparent in review of the final quadrant in our table. Literature has found that for sounds considered noise, this includes traffic, aircraft, rail, occupant, building, and environment, noise tends to be a stressor. But when it is intentionally introduced, it can have positive effects on health. However, for both cases, and I don't mean to sound dramatic here, there's a penultimate assumption that the sound is perceptible. We have to look back at first principles to understand why it's important to acknowledge this assumption. As it is generally introduced in acoustical courses, the study of sound has three parts: a source, a path of transmission, and a receiver. To demonstrate This is demonstrated, in the following animations. In these cases, a sound is generated at a source, and of course, as it travels away from it, its sound pressure level decreases. If the source produced higher or lower levels of sound, these curves would shift upwards or downwards respectively. This would be an example of changing the source. In the case of a barrier, such as a wall, sound will transmit through the wall so long as it has enough energy to pass through, and which is most often the case for most constructions. Sound will then continue to decay in the same way. This barrier is an example of changing the path. If absorptive materials are added, and this applies primarily to medium to large rooms, the curve would tighten slightly. This would also be an example of changing the path because the amount of energy reflected back into a space as sound travels from the source to the receiver is reduced with every reflection. The number of those reflections is primarily why this applies to medium to large rooms, because the sound field in a smaller room, smaller distances, is generally dominated by the direct field. Examples of changing the receiver is one that is much more complex and nuanced, and which we will explore more carefully later in this presentation. However, a person's hearing health, whether they have normal hearing or an impairment, is one example that is more easily understood. Fortunately, these physics are rather intuitive. In saying that, I want to bring your attention to the subject of our previous examples, where we are exploring the behavior of sound, and only that. This is important because acoustics is most often understood to be in relation with the person when it is not. However, in our previous examples, we've shown an interest in understanding the effects of sound and noise on the person. The study of the perception of sound and the associated physiological effects is known as psychoacoustics. What may be the most important principle tying acoustics and the occupant together is a principle known as the masking effect. Trust me when I say its importance is extremely understated. It has roots that can be traced back to the development of the telephone by the Bell Labs in the early 1900s as part of speech intelligibility theory, and it was later adapted and applied to the built environment in the years leading up to the 1950s. This is relevant because our ability to perceive, discern, and identify a sound has much less to do with our lower hearing threshold and much more to do with the existing acoustic environment and the energy which always exists, just as we can now see on our animations. The extent to which a sound is masked by the existing environment will determine whether a sound is audible, discernible, or intelligible. It is for this reason that we sometimes turn on a fan or a radio when we're trying to drown out noise or to go to sleep. To adapt the masking effect in speech intelligibility theory to the built environment, acousticians considered its inverse. That is, the degree to which speech became unintelligible between two positions in space. As speech becomes less distracting, disturbing, annoying, intelligible, or audible, we essentially have a greater degree of privacy. Now, you may be wondering why we're leading into a conversation about speech privacy, because many people believe the concept is a niche application, one more relevant to corporate, government, healthcare, and higher security environments. There are at least two reasons why. First, speech privacy metrics are defined and measurable. They are the most reliable psychoacoustic metric available to acousticians, which can be used to set expectations in design and to assess the performance of a space. Second, speech privacy, or more generally speaking, acoustical privacy, is strongly correlated with acoustical satisfaction. This is a conclusion that's been understood, certainly anecdotally, for hundreds if not thousands of years, and one that's been more carefully investigated by the late and respected acoustician William Cavanaugh in the 1960s. Here you can see his work, which presents the low strength and correlation found between satisfaction and the attenuation performance of a wall on the left. You can see the higher correlation with satisfaction and speech privacy on the right. Everything is brought closer within 10 points. And we've since produced substantial evidence to support this. For example, we've learned from the surveys by the Center for the Built Environment that the top workplace complaint for both open and enclosed spaces is a lack of speech privacy. The biggest difference there is in expectations. For example, there's in open plan areas, expectations are satisfied when speech intelligibility is lowered and when noises become less distracting rather than becoming inaudible. As we dive into this discussion about privacy, I need to make a clarification about the term acoustical privacy. It is one that I uniquely use to be more precise when differentiating between other sources of sound and noise that which are not speech. This is important because there is not yet a standardized methodology for acoustical privacy and definitely not a standardized definition. However, it is an effective tool in communicating the physics at play. To support this, I'd like to refer to a Danish study of multi-unit residential buildings, or MERBs, where a group of researchers have collected data annually since the year 2000. and with which they've been able to correlate non-auditory health effects such as fatigue, annoyance, pain, and discomfort. They've correlated those non-auditory effects with sources of noise such as neighbors and traffic. While the purpose of those investigations was to determine the non-auditory effects of noise, they've inadvertently demonstrated the importance of acoustical privacy to our health and well-being. This table shows the correlation with the degree of annoyance, or alternatively, a lack of acoustical privacy, with the degree of non-auditory effects that participants experienced when they were more annoyed with that noise, and therefore more negatively affected. However, the adaptation of speech privacy theory in the built environment is a little bit more complex, but the following nuances are important to understand if we want to develop the notion of acoustical equity. Here we define an environment separated in two spaces by a partition. The first step is to consider the ambient sources, that is, the acoustic energy that actually exists in the space that is generated from building-related systems, services like heating, ventilation, and air conditioning systems, or HVAC, and mechanical, electrical, and plumbing, or MEP or MEP. Acceptable maximum limits for these sources vary according to the space type, function, and their expectations, from as low as 20 dBA to as high as 55. As you can see, we're choosing to be a little bit more conservative in room 2, which could be an open plan area, and even more so in room 1, which could be a private office. We also need to establish expectations for noise resulting from occupant activities such as speech, which is not captured by the previous noise limits. We're going to assume a level of 75 dBA, which is consistent with the sound level for normal vocal effort, and that's for speech. And it would be a general or conservative estimation for typical noise in an office. The second step is to consider the path, the transmission of noise between two spaces. We're going to design the partition assembly to an SCC rating of 45, the most commonly specified number. This means that it should reduce the transmission of noise between spaces by approximately 45 decibels. Other metrics will be discussed later in this presentation. The last step is to consider the conditions at the receiver. Foremost, we're going to assume healthy adults with normal hearing. Next, we're going to determine the received level of noise that is transmitted between the spaces, as well as the background sound level of the existing environment at the receiver. For example, 75 decibels is attenuated by approximately 45. Therefore, the received level of speech is going to be 30 decibels in each room because we have a symmetric situation. Visually, we can already see a difference between the two rooms. We can rely on the masking effect to explore what this means for speech privacy and our perception of privacy. As listeners in room 1 on the left, we will be able to clearly hear speech coming from room 2. This is because the received level of speech in black is higher than the existing acoustic environment. This means that a speaker in room 2 does not have speech privacy. As listeners in room 2, we will not be able to clearly understand or hear speech coming from room 1. This means that a speaker in room 1 has some degree of speech privacy because the received level of speech in black is being masked by the existing acoustic environment. The Articulation Index is the forefather of all speech privacy metrics, and one of the two that is most prevalently used. It is standardized in ASTM E1130. The other is the speech privacy class, which is standardized in ASTM E2638. The Articulation Index is a precise assessment of intelligibility, which assigns weighting to frequencies that contribute more to intelligibility. In contrast, the SPC is a modified version of the AI that does not weigh frequencies in an effort to better indicate a measure of inaudibility. However, there's an additional psychological component not captured by these metrics, having sense of one's own privacy. For example, because listeners in room 1 on the left will be able to hear talkers in room 2, they will assume they too can be heard by listeners in the other room. Similarly, listeners in room 2 will not be able to hear or understand talkers in room 1, and they will naturally assume that talkers in the other room will have a similar experience. I'm certain we've all been in situations where we've lowered our voice as to not be heard by others, or found ourselves in situations where we didn't realize we could be heard. These are examples where our speech privacy and our perception of privacy are mismatched. To this point, we've assumed background noise conditions are constant and unchanging, which is hardly ever the case. One acoustical solution or strategy is to introduce engineered sound, to ensure the background sound level in a space is providing a minimum assurance of privacy. The use of masking sound allows for us to greatly reduce the extent to which acoustic conditions change with respect to time and the environment. It is for this very reason that background sound is considered and often referred to as the most important parameter affecting speech privacy by experts in industry. In summary, this is an excellent example of the fundamental principles we introduced previously. We first looked at the physics. We then considered the psychology and physiological effects associated with perceiving sound. And we got speech and the perception of privacy. It is important that we consider this perspective because sound or noise is almost always considered a stimulus, or as I said before, sound that is perceptible. The sound is dominant in research. By way of an example, the majority of acoustical studies, if not all of them, can be assigned to one of the following two groups. One, surveys of populations near a type of noise source like an airport, railway, or a highway. Or second, investigations that invite participants to a research facility and then subject them to stimuli like white noise or music. In both cases, assessments are made based on exposure, and a measurement is made of the associated reaction. Yet a moment ago, I demonstrated how sound can be a dampener, and I will soon indicate that it is especially effective when it is unobtrusive. I'm hoping my last remark sparked your interest because it relates to acoustical comfort, a notion that many believe to be more qualitative rather than quantitative. However, again, we need to revisit several fundamental principles to demonstrate why this is not the case. I'll begin by revisiting my previous description of sound, being acoustic energy. And while this is true, we experience sound in the form of sound pressure, which we measure in physical units, but we report it in units of decibel. On the following table, you can see the physical units of sound pressure, but for different levels of vocal effort. But then you can also see the associated decibel values. Clearly, the latter is simpler, minimizes potential errors in reporting, and the values are more relatable. I had also indicated that the study of sound consists of three parts: source, path, receiver. The behavior of the physics of sound as it is created, as it travels, and as it is received can be described according to three dimensions: temporally, or as a function of time; spectrally, or a function of its frequencies; and spatially, or a function of our surroundings, or more specifically, the impact architecture has on the propagation of sound. Although these properties of sound are conceptually straightforward, they each have their own complexities, which we will study individually. We'll start with temporal variations of sound, as it is relatively straightforward. Speech happens to be a very complex example of temporal variation. There are peaks whenever I speak words, with momentary lows when I pause between words and sentences. If we pay even closer attention, we observe higher lows and variable peaks when I articulate certain vowels and consonants. So while my average level of speech for normal vocal effort may be 61 decibels, the dynamic range of speech is approximately 30, so plus or minus 15. For these reasons, it makes much more sense to consider simpler sources like a generator. A generator could produce continuous noise when under constant operating conditions, or alternatively, it could produce noise in a cyclical manner, as shown on this graph. It can generate relatively low levels of noise when on standby, and then significantly higher when operating at higher levels or maximum loading conditions. Interestingly, the time average sound pressure level of both these signals, in this particular case, are equal. But in practice, nearly all sources of noise tend to be temporally sporadic. Now, the general population tends to have a little bit of a harder time understanding what spectrum is. That's because we tend to think about everything with respect to time and distance. To give you an example, I'm going to bring up three circles and I'm going to pin them together at their center so that they rotate and move together. As you can see with the help of the markers, the circles are rotating and moving across the screen at the same speed. The centers of the circles travel the same distance in the same period of time. What I'm trying to point out is that people perceive sound with its frequencies in the same way, but this perspective fails to understand the behavior of individual frequencies. To demonstrate this alternative perspective, I'm going to reproduce the same three circles, but this time I'm going to let them each roll freely. Again, the centers of the circles are traveling the same distance in the same amount of time, but we're observing a new behavior. Each circle completes a different number of cycles. To reiterate, the second animation best describes the behavior of sound. Because all acoustic waves travel the same speed, yet each frequency completes a different number of cycles. Therefore, each has a different length or a wavelength. We can take our standard equation and rearrange it to get an expression that describes the behavior of individual frequencies. Just like the scale for time, the spectral range has theoretically no limits. but we experience energy at different points on the spectrum differently. For example, frequency between 0 and 100 hertz is generally experienced as vibration. Frequency values starting at 20 hertz to about 20,000 hertz is experienced as audible sound. The discussion of energy beyond these ranges is outside of the scope and interest of this particular presentation. So although the audible range makes up a small fraction of the overall, it's impractically wide to consider every frequency. This can be seen on this scale, which plots a point at every 10 hertz interval between 20 hertz and 20,000 hertz. With so many data points, the markers look like a straight line. Fortunately, we don't have to look at every single data point because we have a hard time discriminating between individual frequencies. This becomes apparent as we move towards the higher end of the frequency range. This is best understood by visualizing the difference between wavelengths. For example, we're able to visually see a difference between a mile and a yard and a foot and an inch. But distinguishing between various fractions of an inch is significantly more difficult. The higher the frequency of sound, the shorter the wavelength, and the harder it is for our ears to differentiate between individual frequencies. Because of this, we group frequencies into ranges called octave bands, as highlighted in orange bands here. In technical conversation, octave bands are usually referred to as full or 1/1 octave bands. Full octave bands can be further subdivided into smaller ranges, but never grouped into larger because they're already whole. The reason we say full or 1/1 is because these prefixes replace the word fractional in fractional octave bands, where it would otherwise be replaced by a fraction like half, a sixth, a 12th, or etc. However, the most commonly used fraction is 1/3 because of its close ties with human perception. Before I go on, you may notice that the scale changed during my animations. That's because of the non-linearity of the size of these groups, which you can see on the first scale at the top. There are more individual frequencies as we move towards the higher frequency, towards the higher end of this frequency scale. But since these groupings are being used to help differentiate between sounds having different tonal characteristics, we use this new logarithmic scale to show equal importance to each band. At the bottom of the slide, I've provided another scale showing the 1/3 octave bands, or in other words, the subdivision of the full octave band by 3. There's 3 points to every one from the top to the bottom. But while the use of 1/3 octave bands offers greater understanding and confidence in the study of sound, its use is not standard for all applications. One main reason is the lack of funding by governments. We continue to rely on data from a time where technology was limited, forcing acousticians to rely on single value metrics or the full octave band data. Here's a figure from the ASHRAE HVAC Applications Handbook showing octave band spectrum from below the audible range to 8,000 hertz. Its purpose is to help the reader describe the subjective impression of sound that is primarily dominated by a certain octave. To summarize, the spectral characteristics of sound are incredibly important because they provide insight as to how we perceive, discern, and discriminate between different sounds. This conclusion isn't a revolution, but it does force us to recognize the possibility of infinite combinations of sounds, which have infinite combinations of spectral characteristics, and each of them being equal in overall level. Therefore, if we accept that we are surrounded by acoustic energy, then we might be able to wonder what balance of spectral characteristics is most favorable. Just imagine being in the comfort and quiet of your own home. While you might not be able to hear anything, if you pull out a sound level meter, you will record an overall sound level of perhaps 30 to 55 dB. Are you curious to know what the spectrum looks like? The answer to this question would establish a quantitative definition for acoustical comfort, and it is critical to introducing engineered sound in the built environment. In fact, acousticians have proposed answers to this question since the 1960s. A well-known acoustical consultancy published this chart in that same decade, suggesting a range of favorable conditions for background noise. But as you can tell, the range is quite large. Instead, they considered the general shape when specifying limits for noise. In the 1970s, a gentleman by the name of Warnock also considered this question. And so he introduced controlled sound, masking sound, using a sound masking system in an office. He delivered different sounds as seen here. He found that sound having the slope between -5 decibels and -7 decibels per full octave band decay was most preferred by occupants working in that space. When investigating the importance of sound level, he simply reported that persons began to take notice of the ambient acoustic conditions when background sound level was raised beyond 48 dBA, which is about 56 dB. Interestingly, the same conclusions are identified in investigations supporting the development of noise rating systems, such as the noise criterion and the noise rating. These rating systems apply a reference contour, which are approximately -5 decibels per full octave band, to measurements of the existing ambient acoustic conditions of a space. However, these methodologies assume the environment is spectrally neutral. Here are 3 background noise measurements of 3 areas in a building. We apply the reference contour in red at different levels, which is determined by the highest spectral level that would violate the curve as shown by the arrows. However, these noise rating criteria are maximum allowance for normal or the maximum operating conditions of building-related systems as defined by the specifications document for a project, meaning the actual acoustic conditions are never explicitly defined. But we'll come back to this later. But let me just remind you of the temporal variation of the compressor situation. It wasn't until the 2000s that the National Research Council of Canada was able to determine more optimal acoustic conditions, balancing acoustical comfort and speech privacy. The result is the following figure, along with its tabular values between 100 Hz and 10,000 Hz. To clarify, the range in orange, between 160 Hz and 5,000 Hz, is important to the calculation of speech privacy, though there's some evidence to show that the higher frequencies beyond this range are also important. These gold bands below and above this range are important to acoustical comfort and acoustical privacy, especially when introducing higher levels of masking sound. I'm going to wrap up this slide with a clarification. To this point, I've referred to decibels or dB as seen on the y-axis here. In fact, spectral data is and always should be reported in dB. The sum of these spectral bands would give us the overall sound level, reported in dB. However, we are more sensitive to high frequencies than lower frequency sounds. This means that a low frequency sound will have to be higher in level to be perceived as being equally loud as a high frequency sound. For this reason, we've developed the A weighting scale, which is a set of correction values for frequencies that adjust for our sensitivities. We can use that scale to calculate the corresponding A-weighted overall sound level, dBA, to get a better sense of the annoyance that a particular sound would have on us. The data we're seeing on the chart here has an overall level of 56 dB, but a corresponding level of 48 dBA. It's important to not confuse the two. To this point, we've considered 2 of the 3 dimensions, temporal and spectral characteristics of sound. The vast majority of acoustical work requires only use of this information. Yet the acoustic measurements produce vast amounts of data, and it's somewhat impractical to review it all. For this reason, we take averages of measurements with respect to time and spectrum. Our second graph on the right shows a snapshot of the 1, 10, 30, and 60-minute marks. The white line shows the average spectral measurements for that period of time. While this following complex graph presents the reality of the spectral fluctuations of sound from one moment to the next, it gives you an understanding of how much data is really consolidated in these 2 charts. Moments ago, I shared this plot. This time around, I'm going to present you a more complete set of measurements of background noise conditions for this specific facility, which is unoccupied. I'd expect you to be surprised by the extent of the apparent variability. In fact, there's 21 dBA between the minimum and maximum overall levels, with the average being around 32 dBA. The standard deviation, meaning 67% of the measurements, are within plus or minus 7 dBA, a spread of 8 dB. If you assume the rule of thumb, which suggests that a change in 3 decibels is enough to perceive a change in loudness, then you've got nearly 3 changes in loudness throughout this space. Some of you may suggest that the variations in level would never be acceptable in a project. However, the majority of these background noise measurements comply with the second most stringent requirement in Table 1 of ASHRAE's handbook, NC 25. This outcome is possible because these tables, are maximum allowances for noise, not the actual acoustic conditions. The previous chart is one reason why traditional design schemes are ineffective at providing good acoustics, because they address one component or aspect of the acoustic environment. To be more specific, there are 2 schemes which exist, 2 main schemes, acceptable level and categorization schemes. The first specifies maximum allowances for background noise in spaces. These examples include on the left, the WELL standard, the middle, the IGCC, and on the right, the ASHRAE handbook, which may be the most referred table by industry. For example, LEED refers to it as does FGI. I'll also take a moment to point out the highlighted note indicating that background noise is assumed to be spectrally balanced. Beyond these maximum limits, there's loose guidance as to its temporal qualities, and there's an assumption that the background noise measurements are made at the worst and highest risk places in that facility. The second type of scheme specifies required sound insulating performance values for the partitions separating spaces. We can find these tables in some of the same documents mentioned previously. Categorization schemes do not consider the source level or spectral characteristics explicitly. Therefore, it's possible that a partition will not sufficiently provide sufficient attenuation of spectral bands or noise sources. This can lead to under or over specification of partition walls, which may lead to unnecessary costs. Example, in terms of materials, labor, time, or remediation efforts. In case you didn't notice, these tables suggest values for STC, CSTC, and or NIC. While all of these are single value metrics, they each have their own nuances. More specifically, STC, or sound transmission class, is a metric that is calculated from laboratory measurements and intended to report the performance of a product that can be used for the purposes of design. The composite STC, or CSTC, is a calculated metric using STC data, again for the purposes of design. The metric is supposed to reflect the composite performance of the walls, ceiling, floor, doors, and or windows between two spaces. The accuracy of its calculation process and results is somewhat debated between the members in the community. Lastly, the NIC, or the noise isolation class, is a metric that is calculated using on-site measurements. For this reason, the NIC cannot be used for design. Not included here is the ASTC, or the apparent STC, a metric that is more often used in Canada and which is part of their building code. It is a field variation of the STC. Given that STC uses laboratory data, it has become a general rule among acousticians to accept NIC values that are within 5 points lower than the design criteria, or an ASTC value within 3 points. The most common reasons for significant deviations include improper design, inconsistent design, and or poor construction. As you can tell, there's tremendous allowance for uncertainty, one for background noise and one for sound insulation. This further enforces the benefits of using masking sound as an adjustable solution to enhance acoustical performance of a space. Despite these realities, these tables have made their way in nearly every standard, guideline, and building code over the past 50 years. To help the architecture and design community, acousticians and manufacturers have proposed simple strategies to help in design. The most well-known of these strategies is the ABCs of architectural acoustics. However, this abbreviation is only intended to be memorable and to help reinforce the need for a holistic approach to acoustical design. Architects and designers have, unfortunately, by some, been encouraged to step through these ABCs as a fail-safe or foolproof system. First absorb, second block, third cover. Unfortunately, these steps aren't a holistic framework for reasons that we just explored. In fact, the undertone is to fix rather than to plan and manage the acoustic environment in a space. I'd like to move on and share a little bit more information about sound masking systems, their role, and how to implement them correctly. I'm going to start by describing what a sound masking system is. Basically, it's a network of loudspeakers, typically installed in a grid-like pattern, in an open ceiling, or above a suspended one. Out of curiosity, I'm wondering if you can actually spot any in this image here. The zoning and the output of loudspeakers is controlled by electronic devices linked to centrally located panels, and optionally with software. In addition to masking sound, most sound masking systems can also distribute paging and music. I'm now going to point out a couple loudspeakers here. Some systems can also support transducers. For those unfamiliar with transducers, you can see one here, which is roughly the size of your fist. This device serves the same purpose as a loudspeaker, but can be used in applications where loudspeakers cannot. For example, you can install a transducer on rigid surfaces like a gypsum ceiling in order to preserve the ceiling's clean appearance. It can also be installed on doors, windows, etc. to help thwart some methods of electronic surveillance, such as which may happen when someone's trying to eavesdrop. It emits sound by vibrating the surface it is attached to. It converts the surface to a speaker. It's important to note that the vibrations of the surface emit airborne sound, and the resulting acoustic energy is not experienced in the form of physical vibration. We can now go back in time and review the progression of sound masking technologies. More specifically, we can explore the relationship between the limitations in technology and how that impacted design. Ultimately, sound masking systems were first introduced to the architectural space in the 1960s, coinciding with research on the topic. This includes William Cavanaugh's that I mentioned earlier. These systems were primarily were first designed as central systems, meaning a single zone, meaning a single signal was sent out to a large network of speakers. And I trust at this point you have an understanding as to why this was ineffective at improving the acoustical experience of occupants. These systems did not and still do not have the ability to achieve precise adjustment of spectral and overall levels of individual speakers. While advances in technology, cost of equipment decreased and we started seeing hybrid designs, which grouped spaces having similar architectural features, sizes, and expectations. While these realizations were a breakthrough, the performance of these systems still fell short because there are still too few zones. Some reasons which discouraged the design of even better systems include the cost of materials, which were still relatively high, and the installation and field commissioning of processes. The installation and field commissioning processes. The installation and configuration of more zones were more challenging and time-consuming, as was the field commissioning process. With so many zones, it was impractical because those systems had to be manually tuned, and such a process could take anywhere between 30 minutes to an hour per zone. Fast forward to the 21st century. Technology is no longer a limitation, and advances in electronics allow for decentralized architectures and for addressable components within a networked system, meaning there are no barriers to specifying small zones or to installing them. The ability to deliver localized control of sound by decentralizing the generation of sound rather than requiring long runs of cable is now an affordable reality. The final hurdle, field commissioning, is also overcome using software to automate the tuning process. This is able to reduce the time required to tune a zone down to under a minute, 15 to 30 seconds to be exact. But more importantly is the ability to tune with far greater accuracy and precision than is at all possible via manual methods. I hope to bring us a little closer back to theory by reminding us about the purpose for a sound masking system, which is again to introduce unobtrusive sound. We have seen this graph previously, and now we want to strive for this, a sound that is unobtrusive, that is temporally constant, and spectrally balanced. Oh, of course, and spatially consistent. When this is done properly, the second chart is what the environment can in fact look like. On this slide, I've changed the 3D rotation properties to show the extent of the variation of background noise and then of masking sound. It is for this reason that the environment is higher in level and can be perceived, it is for this reason that an environment that is higher in level can be perceived as being more quiet than one that is lower in level. To develop that notion, we can differentiate between two terms that are often used synonymously, silence and quiet. The word silence suggests the removal or absence of sound, and practically this is not attainable in the vast majority of spaces that host more than a single occupant. On the other hand, quiet infers comfort. A room with multiple occupants can be perceived as being quiet if it offers a comfortable acoustical experience. Here's another example demonstrating a sound event like speech or a textbook falling off a desk and the transmission of that energy as a function of time and distance away from the source. When the background sound level is not controlled, the source remains perceptible until it reaches the ambient background noise level. In contrast, when a sound masking system is designed and commissioned correctly, the extent to which that event is perceivable, discernible, or identifiable is noticeably reduced at distances further away. And as you can see, the so-called privacy intelligibility trade-off is misleading because when you put it in a practical context, the importance of intelligibility is generally required in a near proximity, for which there will always be a strong signal-to-noise ratio. In looking at the previous graphs, you may be wondering about tolerances because surely it's impossible to be exact when the physics are as complex as they are. For this reason, it is incredibly important to understand the difference between precise tuning and localized control of a treatment area and a highly academic argument for spatial uniformity within it, which simply cannot exist. This is because the architectural environment will affect the propagation of sound from a loudspeaker, and every environment will affect it in its own way. However, it is within our ability to design a system that allows for localized control and to tune it to calibrate the loudspeaker's output at a position. To determine what those tolerances should be, we could look at speech privacy and intelligibility theory. Here is one assessment using the Articulation Index for a specific environment. For any typical level of masking, such as 46 dBA, a change in plus or minus 2 dBA can result in a difference of upwards of 55% in intelligibility, which is very significant. whereas a change in plus or minus 0.5 dBA is about 10%. To clarify, this graph is showing differences in intelligibility in increments of 1 decibel. So plus or minus 0.5 dBA would actually be between 45.5 and 46.5 dBA. With a well-established understanding of the fundamental principles, we're able to put together a list of best practices for design and tuning. Foremost is the need for small zones. Practically speaking, the treatment area of a single speaker is circular. As sound radiates out. The diameter of a treatment area is usually between 10 to 15 feet, which is up to about 175 square feet. However, sound masking systems are typically designed and installed in grids of 10 to 15 are typically installed in grids which are spaced at 10 to 15 feet center on center. Although this leaves small gaps, the treatment area would then be upwards of 225 square feet. But we need to tie this back to something, and our priority is always the occupant. According to literature, CoStar, NFPA, and BOMA, typical occupant density values range between 10 and 300 square foot per person, depending on the environment and its purpose. For these reasons, it is encouraged that zones be limited to no more than 3 loudspeakers, up to a maximum of 675 square feet. Of course, this is in addition to the limitations as dictated by physics, where localized control of sound is not possible if the system's design doesn't allow for it. Second, each zone needs to be supported by a dedicated sound generator, which by very definition is required to allow accurate and precise adjustment of 1/3 octave band sound levels and therefore the overall level of localized treatment areas. Fourth, the system needs to be field commissioned, whether by the manufacturer or an independent third party, demonstrating that all zones are in compliance. ASTM E1573 is the only reference in the world that can be used to hold parties accountable. And let's not forget, tolerances for commissioning are not an argument for spatial uniformity. To repeat myself, for a sound masking system to be effective, it needs to be designed correctly and field commissioned. There is no way around it, and we've discussed this previously by looking at this chart. It has to be both. Otherwise, the sound masking system is simply going to be increasing the background noise level in that space. The sound field is dictated by the architectural features of the environment. A system that conforms to the previous best practices can achieve the following performance. The data presented here on the right is real commissioning data of that same environment. We're going to wrap things up with the following case study. The American Society of Interior Designers is the oldest, largest, and the only multidisciplinary professional organization for interior designers and interior design students, as well as for the manufacturers and suppliers who support that profession. When it came time to move their corporate headquarters, they chose a new 8,500 square foot office in Washington, D.C., and they were determined to create a space that would reflect its strongly held belief in the power of design, so that it would serve as a model for innovative design. For this reason, they pursued LEED and WELL certifications and became the first in the world to achieve platinum level, the highest level of recognition for both of them. With the help of an acoustical consultancy firm, they accomplished this by using a number of acoustical strategies, which included a sound masking system to plan for and to manage the acoustic conditions throughout their facility. To this date, satisfaction with reduced noise and speech privacy has increased significantly. The overall satisfaction in acoustical quality improved by 92%. Physical and mental health scores have also improved. Collaborative work has increased by 9%. Staff retention is well above their historical standards. Their absenteeism scores, meaning better attendance, improved by 19%. Employees' sense of ownership and pride in their workplace has also increased. And notably, productivity increased by 16%. This yields an estimate of $674,000 to ASID's bottom line in their first year, and is expected to contribute $7 million over the 10-year lease period. This summary demonstrates how a comprehensive approach to acoustical design and performance verification can positively influence health and well-being and occupant satisfaction. And we look forward to further developing these concepts as part of a hierarchy of principles for good acoustics, which certainly includes acoustical equity. We've now reached the end, and I hope you found this course informative. I'm happy to stay on to answer a few questions now or in the future by email. So thank you for your time and for having me.
Hi, thank you, Viken. I had a question to start. when is the best time to address an acoustical assessment of a space? I mean, what's the difference between a space that is being designed versus a space that is already occupied? How can they both be addressed and obtain the same results?
I mean, that's an excellent question. It's for that very reason that many standards like GBI and WELL have structured their criteria in very unique ways. For example, the typical approach, which GBI, USGBC with the Green Globes document and LEED approach it, is by having separate sets of requirements for new construction and existing buildings, whereas the WELL standard is more conceptually effective at a high level. And so you can always approach the topic of acoustics at any period of time, but it's also best to get in front of it as much as possible. So when you're starting to lay things out, think about the acoustical expectations you have for these environments. What degree of privacy are you hoping for? And then you can situate, the different types of spaces with their functions accordingly.
I see. Anybody else have any other questions? Please, you can post them on the questions and answer tab.
So I noticed a couple of people were asking about the slide deck and the certificate. I'll answer the certificate question right away. Please make sure you've signed in or provided indication of your attendance. Those should be passed on shortly after the conclusion of this presentation and will be submitted to AIA within the required period, which is within 10 business days.
Okay. Well, I don't see any questions coming in.
Well, as I mentioned, if questions do come up in the future, I'm happy to answer them by email. My email is above. I'm very grateful for having everyone's hour today. Jose, it was also a pleasure, and I'm very excited and happy that I had the opportunity to show up and to kind of advocate for the importance of acoustics in the built environment.
Oh, thank you so much. Thank you very much. All right. So, if this will be the end of our webinar. Thank you very much for joining us today, and thank you, Viken, for valuable information for us designers. And I'm sure the general public is very interested in this. They don't know it yet. So thank you very much, everybody, and have a great rest of the day. And thank you.
My pleasure. Take care, everyone. Stay safe.
Thank you. Bye-bye.